All right, another fun problem. We got a gecko. He's on a smooth ceiling. I don't see a gecko. Ah, there's the gecko. So he's upside down on the ceiling, and it's due to static electricity. These feet are covered with microscopic hairs. They separate in the positive charge and the negative charge on the surface. It kind of works when you stick into a surface, which they do, but it comes at a cost. These two planes of charge act like a capacitor, but it takes energy to charge them. Doubling the amount of charge on each surface increases the force, which kind of makes sense, but it also increases the energy required to separate the charge. So he's got to pull his feet off with ever greater force and energy to the poor little gecko. So this one's tough. I hope you can kind of bear with me on this one. We have an equation of U of a capacitor, which is easy to find in your little formulas, and it's 1/2 Q change in V. Well, capacitor isn't in there. Capacitance isn't in there, at least with charge. The other one has capacitance in it, but no charge. So what I'm going to do is I have another equation that says change in V equals Q over capacitance. Everywhere I see a change in V, since these are equal, I'm going to go the capacitance, energy capacitance equals 1/2 Q, and then I'm going to put a Q over C, and doesn't this really just turn into the UC equals 1/2 of Q squared, Q squared over capacitance. So what's going to happen when you look at that? When this Q squared doubles, it's 2 squared, the capacitance stays the same. So what happens is the energy of this capacitor, or the energy required to move charges around in this capacitor, goes up by a factor of 4. So that's kind of a fun little substitution problem. Woo woo, woo woo.